And after that, she was a postdoc at the TIFR Center and in the University of Paul Sabatier, Toulouse, France. And her research interests are mainly in the optimal control and game theory problems governed by nonlinear PDEs. Okay. So today she is going to talk about coupled systems of phase field models and optimal control. Over to you, Sheetal.
Thank you, Sandeep. I hope you are able to see my screen.
Yeah, sure. Yeah.
Okay. Yeah. So I'm at home today and there might be some instability in the network. So I feel sorry for that, but anyway. Okay. So let me start. First of all, thank you very much to Praveen and Venki for this wonderful idea and putting up a conference.
Is it in the full screen mode?
Yeah, I will make it in the full screen mode. Yeah, is it now in the full screen mode, Sandeep?
I think so. Yeah, you go ahead, answer. Yeah. I hope everybody is able to see. Yeah, please go ahead. Yeah.
Yes, so thank you very much for the invitation to talk in this conference, which is tribute to Professor Vasudev Murthy. He was a very generous person. I have never directly worked with him, but we have had a lot of discussions in the TIFR Center, and he was, I was in IISER, and I had a lot of friends in engineering departments of IISER, and all of them used to be extremely appreciative of Vasu, mainly because he used to be very helpful to them. And in one of such occasions, I remember I had a discussion with, I was having some discussion with him. I asked him, why do you spend so much time telling engineers what is happening? And then he used to, he had a very remarkable comment at that time, which I remember very well. So what he said was, see, computer is a machine. You put in something, something will come out. It should not happen that it is garbage in, garbage out. So they should know what they are doing. And that's why I feel it's important that they understand and appreciate the mathematics behind it. So, I mean, in that sense, he has helped. I'm sure there are so many, I personally know so many people in the engineering departments of IISc who have told me that Vasu has helped them during their thesis and all. So in that sense, he was a very genuine person, very gentle person. And of course, all of us remember his humor also. So it's a very, I mean, it's an honor to talk in this conference, though I don't hope that any such things happen to anybody more. Anyway, so let me start with this thing. Are you able to see my screen?
Yes.
Sandeep?
Yes,
I
yes.
have changed the screen. Yeah, I had a doubt. Okay. Fine. So I'm going to talk about phase field models. So let us look at what are the phase field models. Mainly, it is basically the binary fluid, which means you have a mixture of two fluids, which is evolving in a, let's say, two-dimensional domain. And one of the very earlier description of such a model of the binary fluid flow is given by Hilliard somewhere in 1921-22. And it's basically the two components of the binary fluid. And so what happens if the fluids are immiscible, like oil and water, immediately, spontaneously, without you doing anything, that is what I mean by spontaneously, they will separate out and they will form two domains of the pure fluids. So this particular phenomena is given by this Hilliard equation. So the equation goes like phi is a concentration. So phi is basically denoted as, let's say you have two fluids, one of the fluids concentration is phi 1 and other is phi 2. So I write phi as my phi 1 minus phi 2, so that I reduce the number of equations I have to write. And in terms of that relative concentration, I describe the evolution. So phi t is given by diffusion of a particular term. This particular term, what you see in the bracket, is also physically relevant, and this is basically the chemical potential of the system. So so then what happens? So this binary fluid, which is going to which is separating automatically or spontaneously,
So
is
Sheetal, is the
called a
screen
phase
moving?
separation.
Page is moving?
Yeah. Hello.
Okay, I don't know. I'm unable to see. I'm still in the first page. So I don't know. What about others? Not moving. Yeah. 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 Now it is moving. Yeah. Hello.
It's the internet.
Hello. Sheetal, can you hear us? Here.
Yes, I can hear you.
Yeah. Yeah. So now now the screen has moved. Yeah. To the second page.
Okay.
Yeah.
Yeah. Okay. So I don't know if I cannot manage with the full screen. I will just try to give it with this. I'm sorry.
Yeah.
Okay. Yeah. So these phase separation phenomena is very important in fluid flow equations. Basically, it actually, as I said, it is mixing of the alloys or the soft matter mixtures, even the bacterial growth or the viral growth, where you can think about the virus as one of the fluid or the bacteria as one of the fluids, and the surrounding fluid, water or whatever the concentrated material people use as another fluid. And all these things can be or the tumor growth, basically tumor cells and surrounding cells can be also treated as two mixtures of fluids. And so this Cahn-Hilliard equation actually is very useful in modeling such things. But it is not only the Cahn-Hilliard equation which is sufficient, because we also want to look at the dynamics, how it is flowing, and hence one needs to actually couple this Cahn-Hilliard equation with some kind of the fluid flow equations. So we can choose, depending upon the application, depending upon the model, we can choose different kinds of fluid flow equations, let's say Darcy flow or the reaction diffusion equations, or as famous as the Navier-Stokes equation, which can be used to couple with the Cahn-Hilliard equation. So you can imagine once you couple this, all these are nonlinear equations, and when you are coupling it with Cahn-Hilliard equation, the concentration quantity also gets coupled with the velocity quantity in a nonlinear fashion. So that is why it is a coupled system, and which is nonlinear. So in this particular talk, I will look at two important models, Cahn-Hilliard Navier-Stokes model and Cahn-Hilliard Brinkman model. So what is a Cahn-Hilliard Navier-Stokes system? So you can, I'll go back to my first slide where I had written that the equation now is phi t plus u dot gradient phi equal to Laplacian of mu. So you look at this phi, again,
Sheetal,
phi
again it's not
concentration.
moving. Again, it's
Screen
not
is not moving?
No.
No?
No.
I am on introduction page. Are you seeing the introduction?
Yeah, introduction, that equation, what is that kind? Yeah. Now it moved to the,
Yeah. Is it okay if I show it in this particular fashion?
Yeah,
without
sure.
going to the full screen, because then I'm not able to actually see. Yeah. Is this fine? I'm sorry.
Yeah.
Because then I can at least keep track of what is happening. Otherwise, I don't see my screen. And yeah. Okay. So so this phi is basically the concentration as it is in the Cahn-Hilliard equation, and u is the velocity of your fluid. Again, phi is a relative concentration, phi 1 minus phi 2, and u is also the relative velocity of the fluid. Now, in this particular problem which we have studied, we have considered the non-local Cahn-Hilliard equation, non-local Cahn-Hilliard Navier-Stokes equation. So what does that non-local mean? So if you look at the original Cahn-Hilliard equation, what I had shown here, the potential is like minus Laplacian of phi minus phi cube minus phi. So this particular quantity, which is a chemical potential, can be it is locally defined. One can also think about this as non-locally defining, which means you can define it over an integral. So this is what we have done. We have written mu as a phi minus j star phi plus f prime phi, where a is basically the non-local operator, and it is with a particular kernel, internal kernel j. Okay, so so mu is your chemical potential. So it is similar to what I had shown in the previous slide, but this is more general, and this is more, it encompasses more models into it. So this is phi equation. Your mu gets changed, and the u is your usual Navier-Stokes equation if you look at the left-hand side. But as I said, you will have the coupling with respect to phi. So the right-hand side is mu gradient phi, where mu is your, again, chemical potential with the appropriate boundary and initial condition. This particular equation, it has been shown that it has a existence weak solution and also the strong solution. So what we are interested in is to look at the optimal control problem for this particular equation. So what do I mean by optimal control problem? I want to look at the equation and control the velocity by an external forcing so that I can actually take the system, take the velocity and the concentration to the desired concentration and desired velocity. So this, this u, which is written in the velocity equation, is going to work as a control. So what is the aim of the control problem? With respect to this particular equation, the solution of the equation, we are going to define some kind of cost, and we want to minimize that cost. So you can look at this, the simplest cost which I have considered here is a tracking type cost function, which is u minus ud. Ud is your desired velocity, phi d is your desired concentration, and the capital U is your control, which is going to take the system, steer the system towards your desired ud and phi d. So what one wants to do is, we want to do it, we don't want to spend too much in achieving this desired profile. So in that case, what one wants to do is, we want to actually minimize with respect to j. I would like to mention that there are many other cost functionals which can be used and which are used. We can also do a time optimal control. We can also look at only the concentration equation control. So there are various things which are, so here I have considered the L2 norms. One of the very important thing which is from the application viewpoint is the L infinity control, which is very difficult thing. But anyway, I mean, we will stick to this tracking type cost functional, which is L2 kind of function. I have taken the square integrable thing. Okay, so so this particular subject to this cost functional minimization is what we want to do subject to our Carnelian Navier-Stokes equation. So we need to first talk about the existence and uniqueness, and for that, because we have the divergence condition, as in the case of Navier-Stokes, we will define some divergence free spaces, and for the concentration, we will look at our L2 and H1 space. It is not H1 0, concentration is not 0 on the boundary. So we cannot work with H1 0, it is a H1 space, but we can always consider the integral of, I mean, the mean value 0 functions there. And that is what at various places we have done. So what is, so these are typical operators which are defined in Navier-Stokes existence uniqueness theory. I will not go into too much of details of this. So, and on the kind of functions or the parameters what we have in the system, we have various assumptions. Important assumption is about F.
I think we lost her connection. Other people are able to
Yeah,
hear.
there is some issue, I guess. With,
okay, maybe at her end.
Yeah.
Sheetal, you're muted.
Yeah, sorry, I got disconnected. Yes. Yeah, I was talking about this. Are you able to hear me now, Sandeep?
Yes, yes. Yeah.
So there are various assumptions. The important one of the thing is the f, which is double well potential kind of a function, which is s square minus 1 square is a typical example, and one can also look at the logarithmic thing, which is more difficult to handle. So first thing is, as I said before, looking at the control problem, one has to do the existence and uniqueness, and also to study the control problem, one needs the stronger solution. The regularity of the solution is very important. So, but these results thankfully were available for this particular problem. Very recent results in 2013-14, they have not very recent. These are for 13-14, they have done this. By Fregeri, Grassi, Colli, and there is another group in Italy who have studied these kind of problems for various local as well as non-local Canhilliard systems, coupled with various fluid flow problems. So, as I said, the main objective is to minimize this cost functional subject to the solution of the strong solution of the given system. So UD and phi D are your desired states. And where is your capital U? Capital U, we are going to take it in L2 in time, and its G divergence is like an H1 space, H1 in space. And the main problem is to minimize this J. Now, how does one do it? So there are, in any optimal control problem, first of all, we have to guarantee, or we have to show that there exists such a triplet which will satisfy the minimization. So what is the guarantee? That there will be at least one triplet U star, phi star, U star, which will satisfy my minimization and the equation, right? So the proof is by method of going for the minimizing sequence. So you can first look at some UN, phi n, capital UN, which let's say goes to the minimal of J. Now, J being quadratic helps us because it's quadratic and convex function. So you can guarantee the minima, the infimum is guaranteed. And then you can look at the minimizing sequence, which takes us to its infimum. And then one has to do a lot of estimates, a priori estimates, to show that the weak limits UN, phi and UN will exist in appropriate spaces, and they will also converge to a element U phi capital U. Now you have to show that U phi capital U also satisfies your system, so that you can call that as U star, phi star, U star, which is your optimal control or optimal triplet. So for that, we use a lot of Sobolev embeddings and other things in the PDE theory. Now we have guaranteed that there exists a solution, there exists a optimal control. Now, how do one characterize it? Can we actually, so this is only a theoretical inference that yes, there exists optimal control. The question what we still have is, is it going to be, how can one denote, how can we construct U star in particular? So for that, we have to actually look at the linearized system. So you can imagine when we want to minimize something, minimize a function, what we do is we differentiate the function, and the derivative we equate it to 0. Now in this particular case, we will not be able to differentiate J directly because, I mean, not in the classical sense, because J is defined from some Hilbert space to R. So when one has to look at the Fresher derivative of J, and that Fresher derivative of J will give rise to a linearized variable U phi, the linearized variables corresponding to U and phi. So those variables I'm going to call W and psi, and I write the linearized system, linearized around the strong solution of the system, of the original solution. And one has to show that, again, you have to prove the existence uniqueness for the linearized system. This part is not very difficult. It goes as very well like using the Galerkin approximations. Because it is a linearized system, and we have already shown that the nonlinear system has existence and uniqueness, and also the strong solution. So this part follows using the earlier results, except we need to do some more estimates. Next, we come to the characterization of my U star. How do one characterize the U star, which we have already found that it exists? So what is the U star? So it is called the typical thing in optimal control theory. It is called an Pointryagin maximum principle, which says that if you have an optimal solution, then the optimal solution also satisfies a certain inequality, and that inequality helps us to characterize U star as a adjoint variable, U star in terms of the adjoint variable. So I will quickly go to what is the adjoint system. And adjoint system, as you know, will be the linearized system in the adjoint space. So this is your adjoint system corresponding to the given J minus P. So you can see it looks similar to what we had earlier. But you will have U minus UD, and this U is your basically the strong solution of your original system. Just give me a 1 minute. Sorry, there is some temple festival going in the background. So, so the adjoint system is again a linearized system. One needs to prove the existence and uniqueness of the solution for the adjoint system. So again, because it's a linearized system, one can actually prove that with some work, and we have to actually prove the strong solution also for that, and we have done that. But what I'm more interested in showing you how this Pointryagin maximum principle work, or this particular the optimal control, how does it satisfy this particular equation 17 and 18 is what I will just sketch quickly. So what we do is, as I said, you look at J as a function of capital U, and you want to differentiate J with respect to capital U. So we do the pressure derivative. So you do f of J as a function of U. I'm going to denote by script f. And then what I want to do is I want to find the pressure derivative. So f of U star plus lambda U minus f of U star is what I calculate. And when we do this, we deduce that it looks like this. And then, yeah, so I have written only f of U star plus lambda U minus f of U star, but we want to divide it by lambda and send lambda to 0. So you can see here we get lambda square, some lambda here, and that is what is going to remain in the system. So we have shown that the linearized system, which evolves from U star plus lambda U, or which has U star as your forcing term, that when you are dividing it by lambda, it goes to actually your linearized variable W. And same thing happens for the phi variable also. When you have phi U star plus lambda U minus phi U star by lambda, that will go to psi. So this particular lemma helps us to write whatever we have here. You see here what we have is phi U star plus lambda U minus phi U star divided by lambda is what we will have, right? So it helps us to write that, and we end up getting the equation which looks like this. So this particular equation is adjoint equation, and hence one can actually get that adjoint equation, the adjoint equation, which is P is what my adjoint variable is, adjoint equation. And these two terms are going to get cancelled, and only U minus U star term will remain. So this particular thing is U. The right hand side of this particular adjoint equation is U. So what we are going to remain only with is UPT plus U star. And when you want to equate it to 0, as I said, when you want to equate the derivative to 0, automatically we are going to end up getting U star to be equal to minus p. Okay, so this is what the sketch of the proof for deriving the U star is. Okay. So now I will move on to the Canhilliard-Brinkman system. So when we look at this binary fluid moving in a porous media, the UT term actually vanishes. So it is no more the Navier-Stokes equation with which we are actually coupling. We are coupling with Stokes kind of flow, and that is that these particular equations were first derived by Brinkman by using the Canhilliard equation as the base equation, and this work is done sometime in 1950s by Brinkman. So this is the typical Canhilliard-Brinkman system, and one has to, so you can see the, like earlier, I am also considering the non-local system with mu to be equal to a phi minus j star phi plus f prime phi, and I consider the same f s square minus 1 whole square. So for this particular equation, because their UT term is not there, the complications are more in the system. First of all, there was no work of the existence uniqueness work is done only in 1920. Existence of weak solution was proved by Grassi and Fregeri and all. The strong solution, which is necessary to discuss the optimal control, was not done. So first what we did was we looked at the strong solution. So to prove the strong solution, as one can understand, we have to, again, like earlier, our main aim is to study the control problem, and H is what is your going to work as your control. So, but to get the strong solution, we need to increase the regularity on H. And in fact, we also have to have a T regularity of H, which was not necessary otherwise. And we do that, we consider this. I have directly written this as a U because that is where my capital U or the control is going to live. And then we have proved that it has a higher regularity. It is L infinity in time for phi. And U is also H2, which is expected, but not very obviously possible to prove unless you make a lot of calculations. Okay, so then again we define, like earlier, the tracking type cost functional, phi minus phi d square plus U minus UD square plus whatever happens at capital T and UT square. Now I have added this capital T term because only in so the equation doesn't have UT derivative. Okay, so that is why it is necessary to consider this kind of cost functional here. And under the assumption of the boundedness, closeness, and convexness of the set, where your U will vary, we have already taken this U, and you can see that this is the admissible control set, and it is a Banach space with this particular norm. So, so you take a closed convex subset of this Banach space, and then we can work in it. Obvious reason why we want to close convex set is because we want to minimize the J, and I want the minima to exist somewhere. Okay, so so the again, like in the previous case, we have done all the steps. We have proved first that the optimal control exists. Then we have tried to characterize the optimal control in terms of the adjoint variable. So after that, there is one more step which can be done. So that was a Pointryagin maximum principle. Here it is another method of looking at it. In some sense, these two methods are same, but these are the two main approaches which are used in control theory. So instead of looking at directly the J, you can look at the control to state operator, which means for every capital U, I'm getting this solution phi U. Now I look at, is this control to state operator differentiable? And if this control to state operator is differentiable, if I can show that in some sense, differentiable in the Frechet sense, because it's not again usual calculus S. So if it is differentiable, then that one will also allow me or help me to get the characterization of my U star, because that is what will be my U star if I differentiate and equate it to 0. So first step is to show that it is differentiable. So as I mentioned, we have proved the first all these things, and lastly we have proved that this S is control to state operator is differentiable. So for this particular case, we had to increase the regularity of F. Again, the S square minus 1 square condition, whatever I have chosen, that works, that fits in this C4 assumption. But still, technically, I need more regularity of the F. So the under that condition and usual assumptions which I have already had, we can show that S is a pressure derivative. And what is the derivative? Now here it is the interesting thing. What is the derivative of S? So S is a map which takes U to the solution of the equation. And what is the derivative of that equation? That thing? So derivative of S prime, I mean the S prime U tilde in the direction of U is basically the solution of the linearized system with control U. So it is psi tilde W tilde with the linearized system controlled by U. Okay, so this U comes into picture in the right hand side of this equation, the equation satisfied by psi W and psi tilde and W tilde. So then again, as I said, that once you equate it to 0, psi prime U tilde, you equate it to 0, you will end up getting U tilde to be equal to, U tilde to be equal to minus of P. Again, like in the previous case, we will be able to characterize the U star in terms of the adjoint variable. Okay. So again, one has to remember that the adjoint variable is always a linearized variable, or the linear, it solves always the linearized system. In that sense, it is a linearized variable. Okay. So this is what we have done in last 2 years or so, and recently I have started working on it's a very preliminary work. Recently, it's very recent. So it is basically 2 months back we have started working on finite element analysis for Navier-Stokes equation. So it's an ongoing work. What we have tried to do, you people have heard a lot of talks about finite element analysis till now, so I don't want to show my ignorance here. But what we have tried to do is we have discretized the space in, they've taken the finite dimensional space and take with piecewise smooth polynomials, and we have tried to prove the a priori estimates with higher regularity, H2 regularity, and phi t also with other with Laplacian regularity, and we have shown the boundedness of this. We still are, the preliminary higher order time regularity estimates also have been obtained. I'm not included it. So as I'm very novice to this field, we are still working on finding out what is the sufficient convergence order we need, and what we see here, it is OH square we are able to prove, but is it sufficient or not is not clear. And we are also planning to do the numerical implementation, and towards that end also some basic things have been done for very simple geometry. So that is all I would like to say, and I would like to thank you. These are a few of the references, and I would be happy to take some questions.